Okay, we're going to do distribution of sample mean scenarios. In other words, we're going to talk about central limit theorem as it applies, okay? So we're going to scroll down because this basically here you can read. This is the calculator commands, etc. Make sure stats test, z test. So suppose that the outstanding credit card balance for young couples are normally distributed. This is key, all right? Because it's normally distributed, I can sit there and go central limit theorem applies regardless. So in which case I can use z equals x minus mu over sigma, or if I'm talking about a group or an average, I can use z equals x bar minus mu sigma divided by the square root of n. Both of those can be applied depending on what we're working with. Regardless of the sample size, I can use this because the underlying population is normal. If it's skewed, I can only use this if it's 30 or larger. So suppose that the outstanding credit card balance is normal with a mean of 650 and a standard deviation of 120. Mean of 650, standard deviation 120. What's the probability that an individual, so in this case we have a sample of size 1, has a credit card balance in excess of 1,700. So we want the probability that x is greater than 700, which, because we're working with a sample of size 1, we would normally use this formula. Probability that z is greater than, and let's go ahead and draw our picture. Our mean is 650. 700, and we know that we're shading to positive infinity because excess means greater, so we're looking at greater than 700. So we're shading this way. So we want the probability that z is greater than 700 minus 650 over 120. And if I go to this, I should be going, oh, well, this looks like a norm CDF. And so with a norm CDF, this is what I plug into the calculator. My lower part of my shading is 700. The upper part of my shading is infinity. My mean is 650. And my standard deviation is 120. So here we go. Second vars, normal, CDF, lower bound, 700. Fill it up with nines, mean of 650, standard deviation of 120. And I end up getting 0.3384. And that's my answer now to receive full credit. But I says to myself, I wonder, could I use stats test and use this formula and go and just use the 1? Well, let's try that out. If we were doing that, there's still the greater than probability that x is greater than 700, which yields the probability that z is greater than 700 minus 650. Everything's been the same so far, over 120, divided by, because we have now to adjust for the sample size, the square root of 1. Let's see what happens. Let's just try that out. So if I go to stat test, z-test, press enter, and I have a mean of 700, a standard deviation of 650, a standard deviation of 120, an x bar of 650, and a sample of size 1. Now I need to be careful here. Which way did I shade? I shaded up, so I need to make sure I have the greater than symbol. And guess what? I put something in incorrectly. Stat test, Z test. Oh, I'm sorry. The mean of the population was 650 and the X bar was 700. I should have written that down. So one of the reasons that really helps if you sit there, and by the way, you're going to be required to on a test, right? Mean 700, standard deviation 120, X bar is 650, standard, and then N equals, in this case, 1. All right. Everything looks good now, and we get exactly the same answer. So it actually does work. So if you want to use stats test, you can go ahead and do so. It actually works for both. All right. So in a simple random sample of 20, so now we have a group. What's the probability that the mean outstanding credit card balance exceeds 700? All right, so we still have exceeding 700, but now we change from a sample of size 1 that we had over here to a sample of size 20, and let's see what happens. So we're still going to have a probability that X is greater than 700. Yields the probability that Z is greater than 700 minus 650 over 120 divided by the square root of 20. My picture is exactly the same. It's exactly the same picture because we're still working with a mean of the population of 650. We're still looking for 700, and we're shading up. Now, technically, if I were a better drawer, this would be taller and skinnier. So let's identify our components. Our mean is 650, the mean of the population. The standard deviation of the population is 120. The standard deviation of the sample, not the standard deviation, the sample average or the sample mean is 700. And then N is 20. So here we go. Stat, test, Z test. Mean is 650, standard deviation 120, 700, and N happens to be 20. We don't have to put the square root of 20 in, we just put 20 in. We need to make sure we have a greater than because we shaded up, and we calculate. And we end up getting a value of 0.0312. So guess what? As my sample size increases, the probability of having a group of 20 with an average over 700 is much less than the probability of an individual. I want to show you something else on the calculator that you can do out of curiosity for yourself. I went back to Z-test. I'm not going to change anything about it, but instead of calculate, I'm going to ask it to draw and see what happens. And I should have cleared my y equals, so I need to go to the second stat plot. There it is. So there's my little area, there's my shaded upper area, and we see our z-score, and we actually see our little probability right here, okay? So it'll actually do that. This is something I should have cleared out, but I didn't do, so sorry about that. All right, so second quit, and let's work this last problem. So now we have a larger sample. Because I have a larger sample, I think it's less likely, or it should be less likely. So this probability is going to be much smaller this next time. So let's try this out. Once again, we want the probability that X bar is greater than 700. Why is it X bar? Because they're asking about the mean. So make sure you pay attention to that. There's a probability that Z is greater than 700 minus 650. So far, nothing is changing. That's kind of nice, except I have to use a different sample size. Our picture should be a lot taller, but it's otherwise the same. The mean is the same at 650. This is at 700. And of course, it's going to positive infinity or negative infinity. And mu equals 650. Standard deviation is 120. X bar is still 700. And then n is now 40. So we're going to go to stat test, z test, and the only thing I have to change is my n to 40. And instead of drawing this time, I'm just going to have it do the calculation. And I end up getting probability that z is greater than 2.6352. Equals 0.0042. All right. And that is central limit theorem. So really quickly, I can use central limit theorem if the underlying population is normal, regardless of the sample size. However, if the sample size, if the underlying population is not normal, and we're talking about the means or the X bars or the averages, and we have a group, if n is greater than 30, then we can use it. So n greater than 30, we can use for anything, as long as we're talking about the means, or if the underlying population is normal. Hope that helps, and see you in class.